All right, so in part 2, I want to look at some categories of forces, okay? So specifically 3 categories: tension forces, normal forces, and frictional forces, okay? Now, these are all going to play out differently in different scenarios, but these are different categories. So our first category is tension. Okay, so let's suppose that I had a block over here and it's on the ground, and I attach a rope and I'm pulling on the rope like this. Okay, so if I'm pulling over here on this side with a force, how does it end up pulling over here on the block? Okay, how does it end up doing that? Is it the same amount of force, or is it something different? Okay, well, what we need to do is I need you to imagine that my rope is really like a really loose spring. Okay, so the spring's there, I've got little coils, all right, and then when I pull on that rope, the spring is going to stretch, right? Just like that. And each little bit inside here of my spring is trying to come back together, all right? And so no matter where I pick, it's going to try, and the effort it's using to try to come back together is the same, because the whole amount that it's stretched is uniformly divided inside there, okay? So if I got 1,000 coils, all right, and I stretch this thing 1 inch, then each coil moves 1,000th of an inch. All right, so because they're all spread out the same amount, they want to try and get back together in the same amount. Okay, so let's just talk about these 2 bits right here. So they want to come back together here. All right, that means this guy is going to pull here, and this guy is getting pulled here because they're next to those bits right there. Okay, so each little coil pulls on its neighbor in the same way. Okay, just like that. So when I've got something like a rope, okay, the rope is like a spring that's very, very, very tightly coiled together. All right, and so it's coiled so tightly together I can't see it stretch, but it actually does stretch, but it stretches on a molecular level. So I've got now, instead of coils on my spring, these are molecules, and the molecules themselves are going to spread out just like that, and they want to stay together. So I've got the same kind of situation. These 2 molecules here, they want to come back together, and so they're pulling on either side of them as they try to come together. Okay, so the way this works then is if we apply a force over here, okay, then that means we're pulling on some of the molecules on this side, all right? Well, they're going to turn around and they're going to pull on the ones next to them. And they're going to turn around and pull on the ones next to them, next to them, next to them, next to them. And in the process, whatever force we're pulling over here ends up getting transmitted. Ooh, white was a bad choice. Ends up getting transmitted all the way to my block, just like that. Okay, now on the other end of things, okay, what does the block feel, or what does the other side of the rope feel? The other side of the rope feels the block pulling back over here, and that gets transmitted back and back and back and back and back over here to this side like this. Okay, and so what we have happening then on the inside is these things kind of all cancel each other out, and all that really matters is what's going on the ends. Okay, so anyway, the way that the rope transmits the force is through this stretching action, just like that. Now, if we have, well, let me get rid of all that stuff. That's kind of really messy. Okay, if we've got, like, let's say we have a pulley. Here's my pulley, and I've got a rope, and my rope is attached to some weight and my rope goes over the pulley and comes over here, and I apply a force over here on this side to lift my weight. Okay, so we're going to make a really simple model for these situations, which says that the sort of the springiness, how it stretches, that tension that results, okay, inside my rope is uniformly transmitted around that pulley, so that all the pulley does is change the direction for whatever force we're applying. So we apply a force F over there, and we end up getting a force F over here on this side. Okay, now that's a model because in reality there's some friction, and the friction is going to alter that. Okay, and that starts to get kind of complicated, but again, we got to think about the role of models. How accurate of an answer do we need? Do we need our answer to be 95% accurate? Then this is fine. This is going to work great. Do we need our answer to be 99% accurate? Well, now we might have to consider that the pulley interferes with the rope. Okay. But as far as we're concerned here at our level, we're going to assume that the pulley doesn't interact at all. Okay. And all the pulley's going to do is to change the direction of whatever force we're dealing with. Okay, another category of forces is the normal force. Okay, now this is a very strange description, but what you need to think when you're thinking a normal force is you need to realize what we're talking about is a contact force. Anytime you have two objects touching, you could have a contact force between them. All right. So this is pretty extreme. If you look at this old photograph, high-speed photograph of a tennis ball hitting a racket. And what you can see is that the surface of the tennis racket is deformed, but so is the tennis ball. Okay. And we've got a situation where the tennis ball is going to be pushing onto the tennis racket. So the racket feels a force from the ball, but at the same time, the racket pushes on the ball, so the ball feels a force from the racket. Okay, so they're interacting with each other. And this, of course, is Newton's third law, which you probably remember from high school. Okay. And these two forces are going to be equal and opposite. But so every force, all right, so your laptop sitting on your desk actually causes some deformation in the desktop. All right, and the bottom of your laptop is actually slightly deformed. Maybe got little rubber feet on that thing, and they're going to get swished. But you have some slight deformation of the surfaces whenever two things come in contact. Okay, now the reason we call it normal is a mathematical and a historical one. Okay, so here's my table right here. If I set something on the table just like this, and I want that thing to be at 90 degrees, I want it to be a right angle. Another term for a perpendicular right angle is normal. Okay, so those of you in calculus, Calc 3, all right, are going to run into a situation where you've got maybe a curved surface of some sort here. Okay, and we define that surface according to a small little vector on the surface called the normal. Okay, and the normal gives, it's sort of like points outward. Okay, so if we know where that normal is, then we can explain what's happening with our surface. Okay, now in here we're not going to be dealing with Calc 3 and complicated surfaces that look like a Pringle. Okay, but that's where that term normal comes from. It doesn't mean typical. Oh, it's a typical force. It's a normal force. That's not what it means at all. When we're talking about a normal force, we're specifically meaning that it's the right angle contact force between any two objects that touch. okay? And we're always going to get that. Now, let's look a little more closely and talk about it like we did with the stretching ropes, okay? So underneath, so if we just think about the tennis racket first, I mean, it is actually strings. So we could think about them as molecular springs that are stretching just like that. So let's narrow down and look at this position right here, okay? Now this position, all right, because it's stretching, it's getting pulled here and it's getting pulled here, both, okay? It's getting pulled equally. However, those are not exactly opposite directions, okay? So like inside the rope, if we pull to one side and we pull to the other side, all right, in the middle, all right, if we think about this as a vector, okay, this vector and this vector are going to cancel each other out. But in our case here with the surface, these two vectors are pointed upwards just a little bit. They're not exactly opposite, and because of that, they don't exactly cancel each other out. And so the result is there's a little bit of force left over, okay, and that force is perpendicular to the curve defined by these two vectors here, okay? So I get a little bit of leftover force up just like that. And that leftover force is 90 degrees to the surface, okay? So we say that force is normal to the surface. And the ball is doing the same sort of thing, okay? If we come over here, pick any spot here, all right, it's going to end up getting pulled in different directions. And in this case, it's actually getting compressed, so it's a little more complicated. But the result of that is also going to be a right angle force poking out this way, okay? Now, over my whole curve, let's take a look at those purple vectors there. Over my whole curve, what you end up having is this purple on this side has a perpendicular component, and it's got an angled component. Oops, I drew it the wrong way though. Here, oops, I want to use blue. And on my other side, again, I've got a perpendicular component here and a parallel component there, okay? And so what happens then is these components that are parallel to the surface cancel each other out, and all we're left with is the bits pointing up and out. Okay, so once again we see that the force provided will make a right angle to the surface of interest. Okay, so again, it's a normal force. All right. Okay, so friction is another force that happens when you have two surfaces in contact with each other, okay? Now, let's talk for just a second about a water molecule. So if I got a water molecule, I've got oxygen, and I've got a couple of hydrogens out here like this. Looks like Mickey Mouse, okay? Now, the reason that these hydrogen molecules stay with the oxygen is because they are bonded. And they are bonded by the fact that you actually have electrons from the hydrogen that sort of are coming in and coming back. Okay? Not literally, but kind of. But not, but kind of, but not. Okay? It gets complicated. All right? But they're sharing an electron. Okay? And by sharing an electron, it helps both atoms. It helps all three atoms. It helps the oxygen, it helps the two hydrogen, and it's kind of like by sharing these electrons, they fill their orbitals and they become stable. Anyway, the point is this electron sharing creates a bond of an attractive force between the hydrogen and the oxygen and the hydrogen and the oxygen. Okay, so this electron sharing. Anytime you bring any two objects together and they touch, you're going to get some of this effect, okay? Chemistry, this is referred to as covalent bonding. So anytime two things touch together, you're going to get this sort of effect. So as your laptop is resting on your table right now, you got little rubbery feet there. Okay. There's a little bit of electron exchange going on between the little rubbery feet and the top of your table. Okay. So if we look at the bottom of the rubbery feet, we find that there's these little places like here and here and here and maybe even here, places where the molecules of the rubber and the molecules of the desktop are very close together. Okay, very close together. And at those places, that's where we're going to get a little bit of that electron sharing. Okay, back and forth. And so they're going to bond. Okay, they're going to try and stick together just like the hydrogen to the oxygen. Okay, they're attracted together that way. And that molecular attraction, it's very weak, but that molecular attraction is what causes these things to stick together. Okay, it's what causes our friction. And it turns out, we'll get into the equations of this in another lecture, but the amount of that friction, the amount of that bond, depends on how much you squeeze those two surfaces together. And you can sort of imagine the more we squeeze these things together, then the more you're going to end up with places where we can have that electron sharing because it's just closer together because of the extra force squeezing the two things together. All right. So what happens then is you take these two forces, and if you try to push one of them past the other, then the bonds that you had here end up here like this. They end up turning. Okay. And so now imagine these little bonds are like little tiny rubber bands. Okay. And if you push, then that rubber band's going to stretch just like that. And it's going to try and pull it back. And so what's peculiar about friction is it tries to oppose changes in relative position. All right. So I've got my two surfaces here. If I try to move them, all right, then those little tiny rubber bands are going to pull back. So I'm going to get some resistance to that motion change because of those bonds in there, just like that. Okay. Turns out that there's two kinds of friction. Okay. Well, maybe three, depending on how we want to say it. But two primary kinds of friction is what we call static. And with static, those bonds are sort of like, they're stretched, but they're never really broken. Okay. And static, when we say static, we mean that they're not moving past each other. They're trying, but they can't do it. Okay. The other type of friction is kinetic. And kinetic is when they're actually sliding. We actually have relative motion between the two surfaces, just like this. Okay, we're going to talk about more about the differences between those two kinds of friction another time. Okay. All right. So let's end part 2 here. All right. Got one more part to go.